Hello, everyone. Thank you so much for joining us. My name is Matthew Packwood. I'm director of the Oregon Origins Project. First, a reminder, please silence your cell phones for the duration of the show. We begin by offering a land acknowledgement and a call to action. The Portland metro area and the entire area of the confluence of the Columbia and Willamette rivers is the traditional homeland and fishing and gathering range of tribes throughout the region. We honor the peoples who have cared for the land since time immemorial. Tribes of the Confederated Tribes of Grand Ronde, Confederated Tribes of Siletz Indians, Confederated Tribes of the Umatilla Indian Reservation, Confederated Tribes of Warm Springs, Confederated Tribes and Bands of the Yakima Nation, Cowlitz Indian Tribe, and many others. The Portland metro area today is home to the 9th largest urban Native American population in the US, descended from more than 380 tribes from across the country. Oregon Origins Project is committed to helping lift up and support the peoples whose lands these are, providing in our fall events a platform for their artists and culture bearers to share their traditions and artistic work. We ask you to join us in learning about, honoring, and supporting Indigenous peoples in Oregon and beyond. You can find ways to support local Indigenous organizations at our website, OregonOrigins.org. This event would not be possible without the help and support of many people, and some of them are here tonight. You know who you are. Thank you so much. I also want to thank our event sponsors, the Regional Arts and Culture Council, Reed College Master of Arts in Liberal Studies, Geological Society of the Oregon Country, and the Central Oregon Geoscience Society. My deepest gratitude goes to our earliest and most steadfast supporter, Ronnie LeCroute. Ronnie, thank you for believing in Oregon Origins Project and helping the project and this event come to life. Please join me in giving Ronnie a round of applause. Thank you, Ronnie. Tonight's performance is the culmination of years of work and driven by a love of Oregon's incredible diversity of wild places. Oregonians are known for our affinity for the natural beauty of our state, and this piece is in many ways a celebration of that. The work also acknowledges the impact we are collectively having on our world through human-caused climate change. Following the performance, there will be a presentation by geologist Ian Madin, and then in a Q&A with me, choreographer Makino Hayashi, and Ian at the end. And now, Oregon Origins 7 Wonders. Thank you all. Thank you all so much. We're going to have a little bit of a transition from art to science. So let's bid our musicians and dancers one more round of applause and farewell. So we'll just have a brief pause, and I know there may be some young people who might need to get to bed as well, so we'll just give us a minute. Thank you so much. While we're setting up, I'd like to introduce my friend. Thank you, Ines. Thank you, Keiko. I'd like to introduce my friend and geologist, Ian Madin, who will give a presentation on the 7 wild places featured tonight. Ian grew up spending summers backpacking and rafting in California, Oregon, and Idaho. His love of the outdoors led him to study geology, earning degrees from UC Berkeley and Oregon State University. In 1987, Ian began a long career at the Oregon Department of Geology and Mineral Industries, or DOGAMI, that included work on earthquake and landslide hazards, as well as geologic mapping. For many years, Ian was DOGAMI's chief scientist, and he also served as their interim director and assistant director until his retirement in 2022. Ian enjoys sharing his love of geology with others, including you tonight, working as a river guide and ride-along geologist for Cycle Oregon. Ian recently discovered a passion for stone carving, and you may have noticed his work out in the atrium there. Please check it out if you haven't. It's pretty amazing. These works use rock from the different landscapes we featured tonight. Please join me in welcoming Ian Madin.
Well, thank you for the introduction, Matthew, and thank you for the opportunity to come here and tell some stories about the geology behind the places that have inspired the music and dance that you heard tonight. So if I could get the first slide, we're going to launch right into the first story. But first, I need to tell you that most geologic stories in most places are actually crashingly dull. Long periods of time go by and nothing interesting happens. But Oregon is different. Oregon's landscape is fresh and new and alive. And so we have exciting stories to tell. Stories not only from millions of years ago, but from nearly yesterday in geologic time. And so hopefully you'll find these as interesting and lively as I do. Our first story is about Steens Mountain and the Alvord Desert. So we're combining 2 of the 7 wonders, so you're not getting shortchanged on wonders here. We're going to get all 7 in. And we're starting here looking at a photograph taken from the crest of Steens Mountain. Steens Mountain is about 9,000 feet high, and it is gently sloping on the west and precipitous on the east. Imagine taking a brick 50 miles long and tilting it up on edge, with one side gently dripping off to the west and the other side plunging down to the east. That's what you're seeing here is the steep eastern face of the mountain, taken from the summit, riven by these deep ravines and marked by dark cliffs of basalt interspersed with grassy slopes on the gentler areas. In the distance, you can see the Alvord Desert. This is a broad, flat, that is completely barren, made of silt and clay, swept by the wind, dry as a bone, and completely unvegetated. In fact, people go out here to look for meteorites, because out in the middle of the basin, a little black meteorite's the only thing that's not white, and makes them very easy to find. So this is a really unique and dramatic landscape in eastern Oregon, and there's a great story behind it. And to tell that story, I want to take you on a little mental journey back in time. So if you will, we're going to step down from the mountain onto this little spot here between the base of the mountain and the desert. And we're going to go back in time 12,000 years and imagine what it would be like to stand at that spot. So the first thing that we're going to notice is that we're standing on a beach. Probably cobbles and pebbles, and there are waves crashing on that beach because the storm has just passed and it has kicked up huge waves on the lake that stretches as far as we can see in either direction and almost to the horizon off to the east. This is glacial Lake Alvord that occupied this basin at the height of the last glaciation. During that time period, the climate was much cooler, but also much wetter than it is now. And there was enough precipitation to fill some of these low spots with lakes that were truly enormous. In this case, the lake was 250 feet deep at the deepest and perhaps 70 miles long. If we were to turn around and look at the mountain behind us, instead of this bare rock and grassland that we see today, we would see forests along the lower slopes, and then along the crest of the mountain, a 200-foot thick ice cap with great tongues of ice descending down some of the canyons towards the lake. Again, this is at the peak of the last ice age when things are just about to dry out and warm up. So that if we were to fast forward, say, another 2,000 or 3,000 years to 9,000 or 10,000 years ago, now the lakeshore would have receded a mile away from us, and the forests would have dried up and been replaced by shrubs, perhaps, and the ice would just be a few little patches left along the crest. Another few thousand years, the lake would be almost gone altogether, and the ice would have disappeared, leading to the scene that we see today with this bare, dry desert. Now let's go back 9,000 years ago again, and if we were standing on this site, we might hear a great rumble and then feel strong shaking. And if we were to turn around and look towards the mountain, we would be able to see the ground break along the base of the mountain and the mountainside rise 6 feet in a matter of seconds during a great earthquake. Steens Mountain is what's called a fault block mountain. It grows by successive earthquakes over time, 5 or 6 feet with each event. Can we get the next slide? So now we need to step out to sort of understand why the Steens Mountain is a fault block mountain, how that comes about. We need to step back a little bit and look at a big picture. So I'm going to give you a moment here to orient. Here's our Steens Mountain. That's the long tilted block. There's the Alvord Desert. This is the outline of Nevada. Here's the Great Salt Lake and Salt Lake City, the Sierra Nevada, and the distance, the Colorado Plateau. And over in this area is Idaho. So we are looking across this area that's called the Great Basin. The Great Basin today is characterized by being an area that has no external drainage. All the water that falls in the Great Basin stays in the Great Basin. There are no rivers that drain it out to the sea. And the reason for that is that it is a phenomenon that geologists call the basin and range. That comes about because there is a large body of warm or hot rock underneath central Nevada that is rising in the Earth's mantle. Rock in the mantle is plastic enough, flows easily enough that if there's an area that's warmer, it will rise through the cooler rock like a hot air balloon rises through the atmosphere. And so that entire area is pushing upward, and as it does so, it has to sort of arch, and it gets, the skin of it has to get longer in order to accommodate that arch. The crust of the Earth is not plastic, it's rigid. And so in order for it to stretch, it breaks up into a series of big blocks bounded by faults. And those blocks tip over and slide past each other, which allows the crust to stretch. In the course of doing that, one side of the block becomes a mountain, and the other side becomes a basin on the other side. And so if we look here across Nevada, all of these dark strips are the ranges, the upthrown sides of the block, interspersed by the white patches, which are the dry lake basins that occupy the tilted down portions of the block. So this process that we see happening at Steens Mountain and at other areas here, Lake Abert and Summer Lake in Oregon, is the northernmost extent of this basin and range stretching and pulling apart, breaking the Earth into these big blocks. And like Alvord Desert and here at the Steens Mountain, all of these bright patches were giant lakes during the last ice age, including Lake Bonneville here, which covered 40,000 square miles, the last remnant of which is the Great Salt Lake. We don't know if those lakes are ever going to come back. Human-induced climate change may have stopped glaciations. These lakes may be done for good. But one thing we do know is that these mountains will continue to grow earthquake by earthquake. If we could get the next slide, we're going to move on to Blue Basin. For those of you that haven't visited the John Day Fossil Bed National Monument, highly recommend that you do. Fabulous landscapes out there, and this is one of the most fabulous, Blue Basin. As you approach Blue Basin from the parking lot down here, hiking up this creek, it doesn't look really all that unusual compared to other areas in eastern Oregon. You're walking up a narrow creek, grassy slopes dotted with junipers. But then you come around the corner and the basin opens up, and it looks like you've stepped into the central plaza of some ancient ruined city with towers and spires that are crumbling into dust and fantastic shapes, all of it an incredible pale blue-green color. It's a truly remarkable spot and has a really fascinating and remarkably violent history. So once again, if we want to understand what's happened here, we're going to step back in time. This time we're going to go back 30 million years and imagine what it would be like to be standing at this site at that point. We would be in the midst of a deciduous forest and a relatively gently rolling terrain, probably standing on the edge of a shallow lake. Many of the trees would be recognizable, others perhaps not. There would be wildlife in the forest, which would be oddly recognizable, horses this big and sloths this big. And as we stood there, we might experience all of a sudden an incredible shockwave passing by that would shake the trees and drive the birds into the air and send the tiny horses scattering, followed by a hot wind. And if we look to the west, we would see a huge cloud rising in the sky. If we can get the next slide to orient you to what's happening here. Here's the Blue Basin. We're looking off to the west. This is the Cascade Range, Three Sisters, Mount Jefferson. The big patch of orange out here near Smith Rocks is the Crooked River Caldera. What we experience with that shock wave, with the rising cloud, is the first eruption of the Crooked River Caldera. From a hole in the ground 30 miles in diameter, several billion tons of lava have suddenly exploded into a cloud of ash and gas that's rising into the stratosphere miles and miles into the sky. Around the caldera, so much ash falls back to the ground that it actually flows away in a sheet 100 feet thick at 45 miles an hour, burying everything around it in a cloud of red-hot ash and gas that then comes to rest and welds together into a solid volcanic rock called the tuff. Where we are, 60 miles away, we would see that cloud rising and rising until it filled the sky completely, blotting out the sun, and then we would start to experience a rain of ash, small particles at first, and then larger and heavier. And before long, we would be caught in a blizzard of gritty, hot ash that would crush the vegetation as its weight accumulated on leaves and branches and continue to fall, burying the land in several feet of ash. This is the first of the eruptions that would eventually build that pile of ash at Blue Basin. There were further eruptions from the Crooked River caldera and from other calderas in the area until several hundred feet of ash had accumulated. But the volcanism wasn't done. There was now another phase that laid down 1,000 feet of dark basalt on top of the ash, and then more ash eruptions beyond that. Finally, around 7 million years ago, the volcanic activity stopped. But throughout all that time, groundwater was percolating through the ash at Blue Basin, and it was converting iron in the ash into a mineral called celadonite, named after the Celadon glaze that was a prized pottery in ancient China. And that celadonite is what gives the ash its fabulous blue-green color. After the end of the volcanism, the rivers managed to carve their way back down through the thick layers of basalt and expose the ash. But for the most part, the ash is hidden underneath soil and grassy slopes. In this particular location, as the last ice age waned and the climate dried out here, the soil and the vegetation got thin enough that at one point, perhaps a thunderstorm of unusual intensity parked over this particular location, that Blue Basin, and the rainfall was so intense that it washed away the last of the soil and the vegetation and carved a gully. Once that ash was exposed, it was extremely easy for it to erode, and the gully rapidly grew into the badlands that we see now. The badlands are maintained because the erosion rate is so fast that seeds can't get a purchase and vegetation can't get started on the slope because every rainfall washes it clean again and makes a fresh slope of ash. This also means that the erosion will eventually erase this incredible little canyon, and it will once again return to gently, perhaps a broad bowl with gently vegetated slopes. The good news is that someplace else in this area, there's another slope that's getting ready and primed to start its own gully, which will lead to yet another one of these wonderlands. If we can move on to the next slide. Crack in the ground. It's a fabulous location. I have to thank Matthew for writing this particular part of the music because it spurred me to go out and see Crack in the Ground for the first time in the 30-some-odd years that I've been in Oregon, which is really embarrassing to say because it's just an absolutely fabulous place. Imagine this going on for miles. This vertical walls of basalt, so narrow that you can touch both walls with one hand and you can clamber your way through the majority of this, although this year when we went in April, there was enough ice and snow that it was a little scary at spots. So there's a great story behind this. If we can get the next slide, I want to give you a little bit of context for this. So this image is looking to the south across Crack in the Ground, which is visible here as this dark band that runs across this broad lava plateau off into Christmas Valley. And you can see this great big black stain here. This is the Four Craters lava field, and the history of the lava field and the crack are closely related. There are places where the lava flows into and fills the crack, and there are places where the crack breaks the lava flow. So they are very closely related in time. So again, we're going to step back in time and imagine what it would like to be there. This time we're going back 13,000 years, which is just coincidentally almost the same as the 12,000 years that we were going back before, but there's actually no relation between the two, just coincidence. And if we were standing on the edge of what is now the crack 13,000 years ago, we would really just see this broad lava plain, but it would have a little kink in it. And along the crest of that kink, there would be some cracked rock. Oh, pardon me. Blasting you guys with the laser here. As we're standing there and watching, we would experience another earthquake. And during that earthquake, the eastern side, the part that was tilted down, would drop another 4 or 5 feet. And the crack would open for the first time, perhaps by several feet. Within a few days, we would start to see small eruptions from the areas that were soon to become the Four Craters as magma that had been moving up through the fault system broke its way through to the surface. And at first, there's a lot of gas in this lava, so it sprays into the air like a fountain. And the blobs of lava as they fly into the air are expanding from the gas that's dissolved into them, turning into a foam, and then they freeze into chunks of scoria and cinder and volcanic bombs. And they fall to the ground around the vent, building up the cinder cone. Eventually, the gas is all have come out of the system, and the lava starts to flow away from the craters and spread out across the landscape. And doing so, it encounters the crack. In some places it buries it, in some places it fills it. And then there's another earthquake that opens the crack up to its current extent. So these two events are very closely related. The faulting provides a conduit that allows the volcanic material to get to the surface. And the processes have overlapped in time. If we look off to the south, we can see a bunch of long mountain ranges that are more fault block mountains of the Basin and Range. This is the Abert Rim at Lake Abert. This is the Winter Rim at Summer Lake. This is the Burma Rim. The fault that we're looking here at Crack in the Ground is going to be another fault block mountain, but we have captured it here in its very earliest stages, 2 or 3 earthquakes at most. It's just starting to grow, just starting to break the ground. Most of these faults, by the time we see them, have grown a mountain hundreds of feet high, and there's no longer an open fissure where the fault meets the ground surface. But this one, we have captured at just the perfect moment to see that initial crack that opens up. And someday this is going to grow perhaps into another mountain as fabulous as Steens Mountain. If we can get the next slide. Now we're going to move over to the west side. We're in Silver Falls underneath the cool green forests of the west slope of the Cascades, where Silver Creek flows through a series of deep, narrow, steep-walled gorges over waterfalls that occur wherever it encounters harder layers of rock. Of course, waterfalls are actually fairly common in the Cascade Range because they're called the Cascade Range for all the waterfalls. But what is unique about Silver Falls is the rock that is forming the falls. Virtually everywhere else in the Cascades, the rocks are derived from volcanoes that erupted in the Cascades. The lavas at Silver Falls are what's called Columbia River basalt, which is the most important and significant rock unit in all of Oregon. So we're going to take yet another journey back in time to learn about the Columbia River basalt. And in this case, we don't even have to go to Silver Falls because Columbia River basalt is about 800 feet below our feet at this point here. So let's imagine we're standing here, and let's give ourselves a clear moonlit summer night so we can see what's going on. We're 16 million years ago. As we look off to the northeast, we would see a distant glow and a cloud of smoke. And as it got closer, we would start to hear a cacophony of rumblings and hissings and shrieks as if air was escaping out of a balloon. And as that glowing, smoking front got closer and closer, the wind might blow the smoke away for a moment, and we could see behind it a mass of red and orange and black lava 50 feet high advancing across the landscape, setting fire to the forest when it touches it, boiling the streams away as it encounters them, and coming closer and closer. This is the leading edge of a Columbia River basalt flow moving through the Portland area. Now, because we want to see more and because we don't want to get cooked, we're going to imagine that we can fly 100 feet above the surface of this flow. So as we move to the north, we can see that this is a mile-wide tongue of lava that is advancing south across the landscape. And as we go 5 or 10 miles further to the north, it will meet up with several other tongues and turn into a river miles wide of this moving, flowing lava. 25 miles, 50 miles on, it will expand to the point where it is a sea of lava from horizon to horizon, swept by slow, dark waves as the lava beneath flows and cracks and bends the thin frozen layer of solid lava on the surface. And where that cracks, there'll be little glows of white hot lava exposed beneath it, like little white caps on a dark sea. We'll go another 50 miles, and now all we can see from horizon to horizon is this ocean of lava. Another 50 miles, another 50 miles. Finally, 250 miles to the east, we'll start to see off in the distance another glow. And as we get closer to that, it resolves itself into a wall of fire hundreds of feet high that stretches for 20 miles across the landscape. And that is the crack out of which this incredible body of lava is erupting, being forced hundreds of feet into the air, falling back to the ground and flowing away to feed the sea that we have seen. We can get the next slide. The orange tint, so just quick orientation, Spokane, Mount Adams, Mount Hood, Three Sisters. Here's the Steens Mountain in Boise in the Oregon coast. Everything you see in orange is Columbia River basalt. There were not just one flow, like I described, 100 of these flows. In the Steens Mountain, they're 3,000 feet thick. In the Tri-Cities, they're 10,000 feet thick. In Portland, they're 800 feet thick. When the Columbia River basalt eruptions ended, all this area that you see outlined in orange was a featureless, flat plain of black lava. Over the ensuing millions of years, ongoing earth movements have broken it and tilted it and folded it, and the rivers have carved canyons into it, leaving behind the landscape that we see today. But some of our most iconic locations in terms of scenery, like Cape Lookout, Yaquina Head, and the Columbia River Gorge, are what they are because they're of the Columbia River basalt flows. If we could get the next slide, we're going to move on to the Oregon Dunes. Stretching from Florence to Coos Bay, the Oregon Dunes are a 50-mile long stretch of dunes that extend several miles from the beach back into the landscape. It's an ever-changing landscape of open sand and islands of forest that are in constant battle as the forest and vegetation try to colonize the sand and as the sand tries to expand and bury the forests as it moves. If we want to understand why the dunes are here and not everywhere else along the Oregon coast, we're going to once again need to take a trip back in time. So if we can get the next slide, a little orientation. We're going to start up here at Florence, and we're going to imagine that we are standing on what is the beach today in Florence and looking to the west. What we would see would be a forested coastal plain, the ocean nowhere in sight. We're 12,000 years back. We're once again at the peak of the last ice age. Sea levels are 400 feet lower than they are today around the world. And so in order to get to the beach, we're going to have to take a walk. So we'll walk across the plain here for about 15 miles before we get to the shoreline at that time, which is indicated by this line on the image. As we finally approach the shore, we'd probably walk through a mile or two of sand dunes before we got to the beach, and then we would find ourselves not on a straight coastline as we have today, but we would be on the edge of a great bay that was hemmed in by this headland open towards the south. This is a key to why we have the dunes where we have them. The sand in the dunes originates in mountains in Idaho or Oregon as, for the most part, little crystals of quartz that are formed in igneous rock. Quartz is very resistant to chemical erosion and is very mechanically strong. And so once a piece of rock has rotted away completely, all that is typically going to be left is the quartz. So for every quartz grain that you find on the beach, a handful of rock someplace has disappeared into dust and into solution. That sand is picked up by rivers, travels down the rivers until it gets to the sea, and when it gets to the sea, it's pushed along the shore by currents and waves. Normally, it travels freely up and down the shore, but in this case, it's caught in this big bay here. And then, at the end of the Ice Age, as sea level starts to rise rapidly, all of that sand that is accumulated here in the bay is being pushed onshore by the rising sea and the waves and wind that come with them in order to make the big pile of sand here at the Oregon Dunes. The dunes are ever-changing, but a recent change does not bode well for their future. European beach grass, which was introduced to stabilize the dunes so that people could build houses on them and such, has proven to be extremely effective at stabilizing the dunes and allowing the vegetation to get the upper hand in this ongoing battle between sand and vegetation. And it's quite possible that in decades to come, the areas of open sand are just going to shrink further and further and perhaps disappear altogether. Next slide, please. The last place that we're going to talk about is Meyers Creek Beach, which is just south of Gold Beach on the southern Oregon coast. It's like many of the beaches in southern Oregon, marked by these fabulous sea stacks that stand out because they are rock that is much more resistant to erosion than the surrounding rock. The rest of the rock is eroded away, and these harder bits remain as sea stacks. In northern Oregon, the sea stacks are typically made from volcanic rocks that either erupted locally or in many cases Columbia River basalt that flowed all the way down into the ocean. But in southern Oregon, the sea stacks have a very different origin. They are what we call exotic rocks in two senses. They're oftentimes very oddball types of rock, not just basalt, and they are also exotic in the sense that they have originated someplace far away, hundreds of miles perhaps, and have been transported here by a process called subduction. If we can get the next slide, we're going to now, for our final journey back into the past, we're going to go back some 200 million years, and we're going to be here a while, so hopefully we'll have a lawn chair and some snacks, and imagine that we are kind of floating above the surface of the ocean here just off of Meyers Creek Beach. The seafloor, which you can see here in the modern environment, is relatively smooth and flat, and when it encounters the shallower water, there's this very steep slope. It's called the continental slope. This is the continental shelf. And this red line along the base here is the fault that separates the two. The ocean is cold and dense rock, and it is moving towards the continent in this direction. When it encounters the continent, it actually slides underneath the edge of the continent along this fault in a process that we call subduction. And around the globe, this process consumes ocean crust. Imagine a giant conveyor belt on the floor of the sea that is, it's like being at the airport on the walkway, an automated walkway, and you drop your donut onto the walkway. When it gets to the end there and the walkway disappears under the ground, that donut gets smeared onto the little teeth at the end. So these are the little teeth on the end. And so for the most part, as we're sitting here in our lawn chairs watching things go by, the seafloor doesn't have any stuff on it, doesn't have any donuts. It's cruising along and simply disappearing beneath the edge of the continent and being recycled. But now in the distance, we can see a chain of islands coming towards us, being transported along with the conveyor belt of the ocean floor. And when they get to the edge of the continent, they stick and they scrape off like that donut. And then 10 million years later, another one comes along and another one. And so this is what actually has built out the southern Oregon crust, is pieces of islands and other detritus being brought in by the conveyor belt of the ocean and smashed onto the edge of the continent. So if we take a look, the different colors here represent different bodies of rock that have been transported, in some cases 1,000 miles, to arrive at Oregon and be smashed on top of each other. What this means is that the rocks here are mixed at all scales. And so when we go to a place like Meyers Creek Beach, each and every one of those sea stacks might be a different kind of rock that came from an origin separated by hundreds of miles and millions of years. We know that this process is continuing to go on because we now have a good geologic record of 19 magnitude 9 earthquakes that have occurred on this Cascadia subduction zone in the last 10,000 years. The next piece that's getting ready to come and be smashed onto the edge of southern Oregon is all of California west of the San Andreas Fault, which is only about 10 million years away from being part of southern Oregon. So with that to look forward to, I thank you very much for your attention, and we'll take a break now and do a little shift, and then we'll come back for our question and answer period.
Thank you for sticking around. You can see why Ian is here. That was fabulous. Thank you again, Ian. I was just telling Ian, he has already inspired me so much, but he's given me new information that I actually want to revise the piece now. So there's that. Anyway, Ian's moderating. Have at it.
Do we have any questions about the music, the dance, the rocks? Paul.
A lot of music is so...
I'm going to bring a microphone to you, if that's okay.
Just a question about the relationship between scientific imagination, which, Ian, you do such a great job of bringing us along these, voyages in time, and the imagination to realize through music or dance or sculpture. Is there any connection between those types of imagination? That's my question.
I'm going to defer to the imagination people on that one.
It's a tricky question, right? Because two-thirds of us are not scientists, so we don't have that, right? You're not a scientist.
I'm not.
So we don't have that side of our imagination, right? But what I can say is, I think, Ian, you do have to answer this, but what I can say for my part is that the way you've heard Ian describe the geology is very visceral. And when you go to some of these places, you can see the visceral nature of the geology, and it actually makes you respond to it. If anyone has been to these places, you respond to like a fault block mountain, you respond to a crack in the ground, right? So to fire the imagination, for me, the inception of this whole piece is based on being in those places and having that response and it inspiring like all kinds of ideas. And awe is usually the typical response. We have an awe experience that is just, what do you do with that, right? And this project is an attempt to take that and make something out of it, so.
And I guess, from the perspective of a geologist, although every science requires imagination to think of something that has not happened before. Geology is sort of unique among the sciences in that all the experiments have already been done, and we're poking through the wastebasket where they swept all this stuff that didn't work, trying to figure out what happened. And one of the very first things that we have to teach new geologists, in fact, I'm going up tomorrow to teach this to students at PSU, is how to think about what's back inside the land that you can't see. You just see a little bit, few snips here on the surface, and you have to learn to imagine what those rocks look like underground. And so we spend a lot of time running these simulations in our head of things that we cannot, we can't see a Columbia River basalt eruption because we would all be dead, or experience, the Crooked River caldera. So we have to be able to imagine that based on the facts that we can collect.
Thanks. First of all, thank you. The music was wonderful, the dance was riveting, and the information this is a great night. I have a question, straight geology though. Mm-hmm. We have earthquakes, we have volcanoes still on the planet, but we don't see anything on the scale of what you described when you talked about Columbia River basalt. What happened? Why don't we see things at that scale anymore?
Well, part of the reason that we are here is because nothing on that scale has happened for 16 million years. Something like the Columbia River basalt eradicated all life within its footprint and probably caused a small global extinction. The asteroid that kills the dinosaurs, there's another one of these flood basalts that in the Deccan Traps in India that was associated with the great dying at the end of the Permian. So, there's an old saying that civilization exists, at the whim of geology, subject to termination at any moment, which is absolutely true. We have simply evolved in a fortunate time frame where there have not been any of these massive eruptions, a Yellowstone kind of thing.
Although we're affecting that process, right? The so-called Anthropocene.
We are affecting that process,
yes.
yeah. Uh-huh.
So we might be bringing it upon ourselves.
We are headed back to the Eocene thermal maximum, which lasted for 30 million years. That's why I think it's quite possible that there won't be any more glacial lakes. I think we may have ended ice ages.
Thank you so much for everything you offered here today. I'm curious, I guess, for the artists, how you kind of deal with this like massive difference in scale between geological motion and the movements of the dancers or the motion of the music. Because it's easy to say like 20, 30 million years, but just like actually appreciating that is a whole different thing. Like actually like, I don't know, feeling the depth of geological time. But when you have, dance and music in real time, you're constrained by the kind of the present moment and just the speed of like the performance and, a 45-minute performance. So how do you get across just the like depth of scale? Like how did you approach that, I guess?
How do you approach that? Well, this was challenging for me to choreograph something. Well, I love nature, but like geologic time and then now and then all that. And then how to make something that, the music that I don't know. And then, but something about like, it's always the imagination comes. Like as an artist, that's just like, my imagination goes crazy and then like all over the world and all that. And then that putting to the shape or dance or all that is, I don't know what to say, but it's like, it comes together in a way to make a performance of these sites. And I actually went to see 5 sites from tonight. And it was just like amazing. It's just like mind blowing that I never knew that kind of things exist in Oregon. So that was like a learning process for me too. That like something, unknown, bring something to some kind of art. And yeah, that was quite a process and interesting and then fun. Yeah.
I have to say, I really would love to get inside Makino's brain and hear how she comes up with these movements because, obviously to speak to your question, like geologic time is a conceit, right? It's an idea, right? We don't actually know we can't experience it. Our lifespans are minuscule compared to geologic time. So it's a total creative conceit, right? But part of being an artist is like exploring the unknown, right? And I think Makino and I we benefit from working in abstract forms. Music is a very abstract form, or can be, same with dance. So I think the distance between the idea and the expression is smaller than you might think, but I say that as someone who's a relatively recent geologic convert. So I think the only way I can answer that is the way I express music is a manifestation of my experience in the place combined with the ideas that, by the way, Ian expresses extremely poetically. You're getting a sliver of his talent. It really is just something else. He's half of the inspiration of this work. But so it really is a mix of the inspiration of the place combined with the ideas behind that sort of place shape, and then the artistic impulse, I guess, which is totally insufficient answer, but that's the answer.
I can just be loud if you want to. Yeah. So I've been to Silver Falls several times, and done the 10 Falls hike and all of that, and it's a really awesome place. And I've always wondered, like, what makes the falls like they are? Like we saw in that picture, like there's a big slab of rock overhanging that the waterfall is coming off of, but then there's like this carved out region underneath that slab, and several of the falls, you can actually walk behind them through that carved out region. So like, why is the lower part like seemingly eroded and the upper part, which the falls is coming off of, is like still there? Why are they like that basically?
Oh, I'm so glad you asked that question.
I just want to say, Ian will answer this, but I just want to say, I asked Ian that exact question when I was thinking about this part of the piece, because I was like, what's with this? Why is this here and not here? But
So in our exploration of the Columbia River basalt, remember I talked about it being a featureless black plain. And for most of the time, the intervals between flows were so short that nothing could get reestablished on that surface. It was just a bare lava surface, and then the next flow came over. But there was one break that was a couple 100,000 years long that we call the Vantage Horizon, named after the community of Vantage in Washington, where it was first described. And during that period of time, rivers got reestablished across the surface and laid down several feet of sand and silt and clay, and forests were able to grow across the top of that. And then when the next flow came out, it buried that. And so that alcove that you see at Silver Falls is the Vantage Horizon, and it's made up of that silt and sand deposited by rivers along with the soil. And you can see there's casts of trees in there that were growing when the lava came out. So that's sort of a unique location that we can find all over the extent of the Columbia River basalt, which is really cool because it's a time marker throughout the entire area. But because it's so much softer, it erodes really quickly from the action of the falls.
Can I ask a question?
Yeah.
So same thing, the Blue Basin. It has those a little cave kind of look, like triangle thing, like
In which part?
Blue Basin.
Blue Basin.
Yeah.
So Blue Basin kind of makes these geometrical shapes because it's got layers of harder and softer ash, and then over the 30 million years that it's been sitting there, it's developed cracks that are vertical and evenly spaced and oriented. So it's already been kind of broken up into geometric blocks. So as it erodes away, it tends to make regular shapes as opposed to just, fluid shapes.
Side note, Blue Basin is in fact my favorite place in Oregon. I think it has become one of Makino's when she went to visit it. If you haven't been, everyone knows about the Painted Hills, but Blue Basin in the fossil beds is where it's at. Check it out.
And the Alvord, that's beautiful.
Alvord, yes, of course.
If people were interested in the geology of Oregon and wanted to join a group that focus, Ian or Matthew, what would you recommend?
I would recommend that they contact the Geologic Society of the Oregon Country, which is a fabulous organization that is devoted to advancing understanding of geology and is really focused on making it accessible to everybody.
You can join us tomorrow at Laughing Planet for Rock Show and Tell at noon.
www.gsoc.org.
And here endeth the shameless plug.
Yeah.
So I had a question about the music. I really like the arrangement with the string quartet, and I thought there were a lot of interesting and sort of like almost discordant sounds that were very geologic to me. So how did you end up where? How did you decide on strings as the instrument that you wrote this piece for?
It's a great question. Does it have an answer? Part of it is, with this was a new project, right? Oregon Origins project just started last year, and thanks to people like Ronnie and others, it's growing. But I was thinking small already, even though of course we're dealing with immense structures and time frames and all that, right? And we may someday do something larger, so there was that limitation. It was just a practical one, right? First, I don't know if I can give a justification for the choice of string quartet, except that there's this huge palette of sound possible in such a small group of instruments that doesn't, to me, have so much baggage as other kinds of instruments. And again, this is going to be an insufficient answer, but I also happen to know many string players in the symphony, so it was kind of a natural connection. As you can see, they were absolutely fantastic. But I think there's a case to be made for lots of different sounds to be brought into this mix. To answer your question about like the sounds of geology, honestly, it's, again, I've said this before, but like the distance between the idea of subduction and the creation of a piece of music around subduction, right? You know, subduction is a downward motion, right? So music can go downward. So music can consume itself. Notes can become harmonies. It can become counterpoint. So I'm not starting a school of geologic music, but I would argue for that because there's a lot of math in both processes, right? At least our understanding of that. So I could go on about that, but I'm not going to.
Question. Can tell us more about Oregon Origins and what is this your second year maybe? Did you say?
That's right.
Tell us more, like what might we see in the future? What are plans or
that might lead to a shameless plug, but I'll do my best. So Oregon Origins, the conception of Oregon Origins is very much in line with what we've been talking about. It's about finding inspiration in Oregon's landscape. That landscape is an ancient one. And think about that. The inspiration we get from the landscape precedes us by thousands or millions of years. We see it today, but it comes from that. So I wasn't seeing a lot in art trying to capture that in a way that felt like a language that spoke to the place, right? So Wallace Stegner's idea of a sense of place, right? So my conception of the project is twofold. One is who are the people who have the time immemorial relationship to the land? Those are the indigenous people. So that's one part of the Oregon origins. They have really the most authentic say on an origin of any place. Indigenous people do. So our fall event was, and you can see this on our website, was an entire event platform for indigenous artists and culture bearers from across the state. We're doing that again next fall. You can, well, there'll be more information about that if you check it out. But the second half is the natural history, which is the other ancient quality of this place. So really the premise is, it's really, I guess it's an argument. It's an argument for there is a huge creative wellspring to be had with the times before colonization, even before indigenous presence, right? And that's what really excites me, and that's what this project is all about, is how can we bring that creative inspiration, that cultural knowledge to all of you? And that's really what I'm trying to do with the project, so.
Can you speak a little bit about the collaboration between music and dance from a conceptual perspective? Like, did you have to come up with the music first and then followed by dance, or like, what was the order of the process, I guess?
Yes, I asked him to make music first. It's so much easier for the dancers and me to get ideas. Yes, and then I wanted to do, like kind of like corroborated the music part to tell him like I want, but then what I said once, he was just like, kind of no. So I was like, okay, I'm gonna just let him create what's, in his brain, heart, and I'll just like, okay, I will just take a part of the dancing choreograph, work with the dancers and all that, yeah. When he came to see in the middle, right? I wasn't finished. I wasn't finished the whole piece yet. And he came to the studio and watched the rehearsal, and he was just pretty happy about it. So I was like, okay, great. Yeah. In one part he didn't like it, so he asked me to change some part. But
And you said no?
I wanted it to say no but I was like, okay. Yeah.
Honestly, the fact that Makino was able to respond, like, one can have an idea and believe in one's idea, right? But that another person can relate to that idea and create beauty out of that idea. I'm so grateful that you were able to find a beautiful, meaningful dance language to it. So it was really more of a partnership than a collaboration, because I wrote everything first, but there was some give and take, I would say. Makino asked for a few changes in the score, which were easily done, and I asked for changes in one of the movements too. So there was also a lot of discussion of, like, I'm not going to go full neurotic here, but there were some weaknesses, I would argue, in the music that needed the dance to make up for them. I'm not going to reveal what those are, but so there was some discussion about, like, the balance of the two, right?
Yeah, and actually that part, pretty good. The part you saw the weakness, that I didn't want to choreograph to it, and I did it, and I'm pretty good.
I'm so glad.
How long was your process, your creative process, from the time that you decided to use geology? I know you would have the time that you collaborated as opposed to the time that you were creating the actual music and the dance moves.
When was the first meeting we did? I can't remember.
Surely a year ago. No?
Yeah, for a whole year. Yeah.
There's the whole incubation period, right? It's where we've talked about it, but we're not making, artists have this thing where they say, we're not doing anything, but it's not that you're not doing anything, you're actually making the art by sort of sulking and procrastinating and all, right? And as friends of mine will know, I've sulked a lot about this piece, but honestly, the process goes way back because it starts with the experience of the place, right? Even Makino can speak to that before she started making dance. And then there's that, like, what can you make of this part? So that's a long process. But then the writing for me was pretty quick. It was like 3 months.
Makino, when he approached you, though, to do this about geology, what was your response? Did you think this is going to be weird, or this is awesome?
It was challenging, but exciting. Something new, and then some challenge, new challenge. And then, especially after I went to see the place, I got very excited. Yeah.
The parts in the music where there wasn't any dance, who decided that, like, there wasn't going to be any dance in those sections of music?
Okay, so what he wanted was like in each nature place, he wanted it to dance for sure. And I kind of wanted it to put little movement in those, what's the time?
Geologic time.
Geologic time. But then it might be interested, do it, and then that. So, but then today I saw it, and I was like, oh, I should have done this thing, and I should have done that thing.
Same.
Oh, that is
Same.
like, oh.
I mean, so geologic time, the premise is you're in a time machine, right? Because as Ian has articulated, we're like 3 million years ago, or 13,000 years ago, right? Each of these places is, first of all, unrelated to a lot of them are unrelated to each other, but they're also just like really different epochs. Is that the word?
Epochs, eras?
Eras, periods, all those geologic terms. So the conceit is that we're going from place to place, right? So it was kind of a natural thing to have the dancers pause, although I agree with Makino. I think there's a version 2 of this could be a full 30-minute dance piece too.
But dancers are actually dying. So they appreciate those little break. Yes.
If you were to do this again or add to it, are there any particular geologic processes or locations that you would want to do that you weren't able to do this time?
My list is at least as long as his.
Yeah, watch this space. We have the ideas for a much larger work, possibly taking on the whole geologic history of the state, but that requires resources and time, and so. But there's so much. As any of you who've spent time in the outdoors in Oregon, there's like so many different microclimates and landscapes, and the diversity is just overwhelming. So it's a pretty easy answer there. So maybe we'll do one more, or perhaps we've done them all. One more. Here we go.
Question for Ian. You said you do like geology boat trips and bike rides and that kind of thing. Can you talk a bit more about that?
Well, yeah. So as I was trying to avoid finishing college, I spent 10 years doing whitewater rafting as a commercial river guide in Idaho during the summers. And a big part of what I got out of that was having people on my boat that couldn't get away from me, that had to listen to my geology stories. It was just great. And then about 10 years ago, I decided I was getting older and I needed to get myself in shape, so I decided to sign up for Cycle Oregon and get to the point where I could actually go out and do that ride. And I got on the ride, and it was out in Eastern Oregon, and I would get off my bike to look at a road cut, and people would ride by going, "Are you okay? Are you okay? Are you okay?" And then I'm watching them ride by, and it's just like everybody is just focused on the butt in front of them, and they're not paying any attention to this incredible landscape. So the second night of the trip, I went out behind they have a message board thing, and I put up a little note saying, anybody that wants to know about the geology that you saw, meet me behind the Rider Services trailer at 6 o'clock. And the first day, 2 people showed up. And the second day, 5 people showed up. And the third day, 50 people showed up. And somebody at Cycle Oregon apparently noticed, because next year when I registered, they contacted me and said, would you be willing to, do presentations and stuff? And so for the last 10 years, I've been going on the Cycle Oregon rides every year, and I write blogs about the geology of everything that people are going to see during the course of the ride, and then I give short presentations in the evening, or sometimes, stand up there for an hour and go on and on about what people have seen, because the thing for me about geology and talking to people about it is there has to be something that you can see in the landscape. Otherwise it's just a bunch of dry words, Silurian, Ordovician, granodiorite, all that stuff. It doesn't matter unless you can see in front of you the manifestation of that geology. And last year, Cycle Oregon went out to the Painted Hills, and it was just like, oh my God, this is so fabulous. Everywhere we go is just so interesting. So yeah, I really like doing that.
Okay. Thank you all for coming. Thanks for sticking around. Thank you, Makino and Ian. Thanks to our crew, our wonderful crew. Have a good night, y'all.